Welcome to the deep dive. We're here to cut through the noise, get straight to the core of, well, some pretty complex topics. And today, we're taking that deep dive into solar thermal energy. It's a really powerful part of the renewable energy picture, but maybe one that doesn't always get the spotlight. So our mission today is to really unpack it. What is solar thermal energy? How does it actually work? What kind of temperatures are we talking about? Because it can get incredibly hot. And what are the applications? It's way more than just the solar panels you might picture on a roof. As we dig into the sources you shared, we're going to find some pretty surprising things, like the real differences between solar collectors, how you can actually store this heat for hours, sometimes even days, and how this tech is driving sustainability in ways you might not expect. Okay, let's unpack this.
Right. So to start, solar thermal energy, fundamentally, it's about taking direct sunlight, solar radiation, and turning it straight into heat. And that heat is used for all sorts of applications. It's quite different from photovoltaic cells, PV cells, which make electricity directly from sunlight. Its main contribution, it's not just about clean energy in general, it's actually a bit of a quiet revolution for certain industries. Think about sectors that are usually seen as hard to decarbonize: cement making, food processing, chemical plants. They use huge amounts of heat. And historically, that heat comes from fossil fuels. Solar thermal is offering a pathway, a greener future for them, directly supporting those sustainable development goals.
Yeah, that's a really key distinction because I think most people, when they hear solar, they immediately think, okay, electricity for the house. But what you're saying is this is about direct heat for processes that just, well, gobble up fossil fuels.
Right.
It really expands how we think about solar's role, doesn't it? It touches industries maybe we don't immediately connect with solar power. So, okay, the core of any solar thermal system, that's the solar thermal collector. You called it the beating heart. Yeah. Absorbing sunlight, turning it into heat. Let's start with the most common ones, the simplest maybe, flat plate collectors.
Exactly. Flat plate collectors, or FPCs, they're very common,
Hmm.
pretty straightforward in design. You've basically got an insulated metal box. On top, there's a transparent cover, usually glass, maybe plastic sometimes. Inside that box is a black absorber plate, copper or aluminum, typically, and it has pipes or passages for fluid built into it. And that clear cover, it works kind of like a greenhouse, lets the sunlight in, but helps trap the heat inside. The insulation obviously stops heat leaking out the back and sides.
Okay, so the sun hits the black plate, gets hot. Heat transfers to the fluid, could have water, could be an antifreeze mix that's flowing through the pipes. And that hot fluid then goes off to be used maybe for hot water or it gets stored. What's maybe a common misunderstanding about these or a limitation people don't realize?
Well, one thing is people might think they only work on bright sunny days, but actually they do pretty well even when it's partly cloudy. They can use diffuse radiation, the scattered light, not just the direct sun, and they're quite efficient for what they do, maybe 50–70% efficient in good conditions. Their real strengths are that simple design, they're easy to install, pretty durable too.
Right, so they're like the reliable workhorse for everyday solar heat needs. You see them everywhere, really. Domestic hot water, commercial buildings, heating swimming pools, even helping heat the building itself.
Then, moving up in, let's say, performance and temperature, you have evacuated tube collectors,
Mhm.
ETCs. Their big thing, the defining feature, is a vacuum. It's between two layers of glass tubes. And that vacuum is a fantastic thermal insulator. It cuts down heat loss from convection and conduction massively. Think of like a high-tech thermos bottle, but for sunlight.
Ah, okay, so the vacuum traps the heat much more effectively.
Precisely. You've got this double-walled glass tube vacuum in between. Inside the inner tube, there's an absorber coating and often a heat pipe, or maybe the fluid flows directly through. That vacuum really lets them get to higher temperatures more easily than the flat plates. We're talking maybe 100 up to 150 degrees Celsius, because the heat just isn't escaping as much. Their efficiency is generally higher too, maybe 60–80%, and they really shine in cold or windy weather where flat plates might lose more heat. Again, thanks to that vacuum insulation. They're also quite flexible to install, and a practical point, if one tube gets damaged, you can often just replace that single tube, not the whole collector.
That makes perfect sense, especially,
Yeah.
yeah, for colder climates. So applications here are things like domestic hot water, but also industrial hot water needs, central heating, solar air conditioning even, and those medium temperature industrial processes. The sources do point out, though, they cost more up front, and they are a bit more delicate than flat plates, which I guess makes sense with glass tubes and a vacuum.
Exactly. And what's fascinating here is how these technologies start scaling up. We're moving beyond just hot water to generating really significant heat for industry or even electricity, which brings us to concentrating solar power, or CSP. Now, These systems are different. They use mirrors, sometimes lenses, to focus a large area of sunlight onto a much smaller receiver area. And by concentrating the light, they achieve very high temperatures, easily over 200 degrees C, often much higher, even 1,000 degrees C or more sometimes. This high heat makes them suitable for generating electricity on a large scale or for industrial processes needing serious temperatures.
Right, concentrated the sun's power. The first type here is parabolic trough systems. If you picture them, they're these long U-shaped mirrors, curved like a parabola. They focus the sunlight onto a pipe, a receiver tube, running right down the middle at the focal line. And they usually track the sun on one axis, just following across the sky. These troughs seem like the established workhorses for big solar thermal power plants.
That's a good way to put it. They are commercially mature. The mirrors concentrate the sunlight, heating the fluid in that receiver tube. Often it's a special thermal oil, or sometimes molten salt up to maybe 400 degrees C. Then that superheated fluid is used. It can generate high-pressure steam to drive turbines for electricity, or the heat can be used directly in industrial processes. A really key advantage is how well they integrate with thermal storage systems, which we'll definitely talk more about.
But if you want even higher temperatures, and maybe that round-the-clock power capability, you need to aim higher, literally. Solar power towers. Okay, picture this. A huge field, thousands of big flat mirrors, they're called heliostats. Each one moves, tracks the sun, and focuses the sunlight onto one single point or receiver sitting on top of a very tall central tower. And these heliostats track on two axes, right? So they can be incredibly precise in aiming that sunlight.
Yes, dual axis tracking. It's an amazing feat of engineering, really, coordinating all those mirrors. They reflect and concentrate sunlight onto that central receiver, heating the fluid inside. And here, it's very commonly molten salt to extremely high temperatures. We're talking 565 degrees C, sometimes even higher. Now, this superheated molten salt can then be stored in these huge insulated tanks. So when you need power, maybe after the sun's gone down, you draw the hot salt from the tank, use its heat to generate steam and make electricity. The big advantages. Power towers get the highest temperatures of the main CSP types, which helps with electricity generation efficiency, and they enable really large-scale, efficient thermal storage. This gives you what we call dispatchable power, power you can supply whenever it's needed, almost like a conventional power plant, day or night. The trade-offs, though, they need a lot of land. The initial cost is very high, and running them, managing all those mirrors and the high-temperature systems is complex.
Okay, here's where it gets really interesting. I mean, imagine that. A solar plant still pumping out electricity hours after sunset. It's not just like a battery storing electricity. It's like a bank storing heat, stored sunshine. This ability to bridge those evening peak hours after the sun sets, that's huge, right? It makes CSP potentially a reliable 24/7 kind of power source, not just intermittent renewable. Okay, next type, parabolic dish systems. These look, well, like big satellite dishes, but instead of signals, they focus sunlight onto a small receiver right at the focal point. And often that receiver is connected directly to something called a Stirling engine. They also have that precise dual-axis tracking.
Exactly. The dish shape focuses sunlight very intensely onto that small spot, hitting really high temperatures, maybe 750 degrees C or more. That heat directly powers the Stirling engine attached to it. A Stirling engine is an external combustion engine. It uses the heat source outside the engine to heat a gas, which then expands and drives pistons. It's very efficient at converting that focused heat into mechanical energy and then into electricity. These dish systems can have very high solar to electric conversion efficiency, maybe 25–30% or even a bit more.
Yeah.
And they're modular. You can set up one or many. This makes them good for remote locations, off-grid power perhaps.
That's right, so maybe smaller or medium-sized power needs or remote power. And a nice bonus, they generally use less water for cooling than the big trough or power plants. The downside, though, seems to be storage. They don't easily integrate large-scale thermal storage like the towers with molten salt, right? So maybe not that 24/7 dispatchable power.
That's generally true, yes. Storage is more challenging at the individual dish level. And finally, there are linear Fresnel reflectors, LFRs. These are often seen as a simpler, potentially cheaper alternative to the parabolic troughs. Imagine multiple long rows of mirrors, either flat or just slightly curved. They track the sun, again usually on one axis, and reflect the sunlight upwards onto a fixed receiver tube that runs above the mirror field.
Ah, fixed receiver. That sounds like an advantage. Simpler plumbing, maybe? Since the receiver pipe doesn't have to move with the mirrors. And these can heat a fluid, sometimes water directly into steam, up to pretty high temperatures, too, maybe 250 to 500 degrees C. good for electricity or industrial heat.
Yes, the fixed receiver is a key design feature simplifying things. Their heat collection efficiency is maybe a bit lower than trough, say 50–64%, but they can use land quite efficiently. You can pack the mirrors relatively densely. And they have potential for what's called direct steam generation, DSG, making steam right in the receiver tubes, which can eliminate the need for a separate heat exchanger, again, simplifying the system and potentially cutting costs.
Okay, we've covered a lot of different ways to collect the heat. So what does this all mean for you listening? How is all this heat actually used out there?
Well, the applications are incredibly broad, as we've touched on. For homes and commercial buildings, solar water heating is huge, also solar space heating, even solar cooling sometimes, and integrating passive solar design into the building itself. Then, industrially and in agriculture, providing hot water or steam for loads of processes. Food industry, chemicals, cement, petrochemicals, solar drying for crops is another one. Solar thermal desalination, making fresh water from salt water using solar heat. And even solar-powered pumps for irrigation. And of course, the big one we spent time on, large-scale electricity generation using those CSP plants. But, if we connect this to the bigger picture, the role of thermal energy storage, or TES, it just can't be overstated. It's absolutely crucial for solar thermal. It's the thing that directly tackles the big challenge of solar power, the fact that the sun isn't always shining. Intermittency.
Yes. He hit the nail on the head. The sun goes down, clouds roll in. That's the classic problem. And that's why TES isn't just an add-on. It feels like the absolute game changer for solar thermal. It lets you save that heat energy for when you actually need it. We're talking different ways to store it right. Sensible heat storage, just heating up a material like water or oil or even rocks. There's latent heat storage using special materials, phase change materials, PCMs that absorb or release heat when they melt or freeze, and even thermochemical storage. But that molten salt we talked about for CSP towers, that's a massive practical example of sensible heat storage in action, letting those plants run long after dark. Okay, talking about game changers, let's look ahead a bit. Here's where it gets really interesting. What's coming next? What innovations are pushing the envelope? And crucially, what are the hurdles? What challenges still need to be solved for solar thermal to really take off even more?
There's a lot happening in R&D. People are constantly working on improving the efficiency of collectors, designing new shapes, new concepts. There's really fascinating work using nanofluids, basically liquids with tiny engineered particles suspended in them to improve how well they absorb heat and transfer it. And also developing better selective surface materials for the absorbers materials that are really good at absorbing sunlight but very bad at radiating heat back out, so they trap it better. We're also seeing exciting potential in something called solar thermophotovoltaics, STPV. The idea there is, instead of using sunlight directly on a PV cell, use concentrated sunlight to heat up an intermediate material to incredibly high temperatures. Then you use a special PV cell that's optimized to convert the light emitted by that super hot material into electricity. It could potentially reach even higher efficiencies. And beyond the core tech, it's about integration. Hybrid PVT systems, for instance, that generate both electricity and useful heat from the same panel area. Or integrating solar thermal with heat pumps to make them more efficient. But yes, there are definitely still challenges. The upfront cost, especially for the big CSP plants and the associated thermal storage, is still high. That's a major barrier. The sun's intermittency is inherent. Even though storage helps massively, it adds cost and complexity. Large CSP plants need a lot of land, which can be an issue. Maintenance is ongoing. Keeping mirrors clean, especially in dusty places, is important for performance. And there can be environmental concerns too, like water usage for cooling in some types of power plants, although newer designs and dry cooling methods are addressing this. This raises an important question, really. How can we keep innovating to bring those costs down and make these systems work effectively in all sorts of different climates and conditions?
Those are definitely significant hurdles. The cost, the land use. Are these things we can chip away at with innovation? Or are these sort of fundamental limits that might affect how solar thermal scales compared to, say, PV plus batteries, which are also getting cheaper? But yeah, it feels like these challenges are also where the opportunities lie, right? For more research, more development, finding new materials that are cheaper and more efficient, making thermal storage even better and more cost-effective, designing collectors specifically for certain regional climates, and figuring out the best ways to integrate solar thermal smoothly into our existing energy grids. Well, as we wrap up this deep dive, we've really covered a lot of ground in the world of solar thermal energy, from, the simple flat plate collectors maybe heating water on a roof, all the way up to these huge, complex, concentrating solar power plants that can deliver power day and night. We've seen how versatile it is, the incredible range of temperatures it can reach, and just how vital that thermal storage piece is for making it reliable. It's pretty clear it has a really important role to play in a sustainable energy future.
Absolutely. And if we connect this to the bigger picture one last time, that ability of solar thermal to provide high temperature heat reliably, on demand, even after sunset, that's potentially transformative. Not just for generating electricity, but for whole industrial sectors that currently depend heavily on burning fossil fuels for heat. So maybe this raises an important question for you, the listener, to think about. As the push for sustainable energy keeps growing, how could solar thermal solutions specifically impact the industries or even the agriculture in your area? What new possibilities might that open up?
That's a powerful thought to leave us with indeed. Thank you for joining us on this deep dive into the fascinating world of solar thermal energy. Until next time, keep learning and exploring.